Here is a typical NCEA question from 2008. We've got a north and a south pole and the loop of wire in it, and this is how an ammeter works. And we will see that when a current passes through this loop in a magnetic field, this will receive a twist. It will try and spin dependent on the current. So it says a current passes anti-clockwise through the ammeter. So it's going A, B, C, D, E. The current is going this way. State the direction of the force, if any, on each section of the wire. So if it says if any, that's got to trigger our thinking, oh, maybe there's some points where there isn't a force. So let's have a look. No calculations are necessary at this moment. So let's have a look at the force on the section of the wire AB. Section of the wire AB. We've got a magnetic field, of course, from North Pole to the South Pole. It's a uniform field between the magnetic poles. So we've got a magnetic field going from here to here, and we've got a current going through this wire from A to B. So let's apply our right hand slap roll. The current is going in this direction, the magnetic field from north to south, so the force on that section has got to be down. So we can say section from A to B, the force is down, straight down from there. Let's have a look at the section B to C. That's the end there. Can you see that there is a current flowing from B to C? Remember, it's going anti-clockwise around. There is a current this direction, but this is also in the same direction as the magnetic field. So the force must be zero. And we can see that from our equation, F equals BIL sine theta. And we will see that sine theta, the angle between the current carrying conductor and the magnetic field, the angle theta is zero. The angle is zero. And sine zero equals zero. So we have no force between B and C, so no force. And that leaves us with the section from D to E. So the current then is going this direction, current in this direction. Let's try our right hand slap roll again. Current is going this way. Got to get my hand around it. Current's going this way, magnetic field's going that way, so the force is upwards. So on this side, the force is up. Second part of the question, the total force, and it's in bold, so that's got to make us think as well. We're going to need to know that in a moment. A total force of 0.60 Newton is produced on the wire within the ammeter. Total force equals 0.60 Newton on the wire within the ammeter when 2.5 amp of current is passed through its coil. Calculate the effective length of the coiled wire between points A and B. The coiled wire between points A and B. The magnetic field strength is 0.20 Tesla. Now, something which we have not thought about for ammeters is sometimes an ammeter may come around. This loop may go around several times before it comes out, so we're going to find the total length of this current carrying wire between points A and B. So let's use our equation, F equals BIL, the force on a current carrying conductor is equal to the magnetic field strength times the current times the length. We're asked to find the length, the effective length of the coiled wire. So let's rearrange this equation. Length is equal to F divided by B times I, and we get total length is equal to 0.6 divided by 0.2 times current 2.5. The effective length is 1.2 meters. But the total force on this loop is 0.6 Newton, and the length is 1.2 meter. But half of that force is provided as the current goes through this side of the loop, and the other half is coming down this side of the loop. So half of the force is provided by the current going between A and B pushing it down. The other half of the force is provided by the loop from D to E pushing up. So the actual length from A to B is half of this. So it's 1.2 divided by 2. So the total length on the side AB has got to be 0.6 meters. So always they're trying to add a little bit of trickiness to it. So again, when you read this question, look, the total force, that's the first hint. A coiled wire as well. Those are some hints that something is amiss there. So that's that question, and that takes us up to merit.